it's working, isn't it?
Okay, our next speaker is Carolyn Zhang from Harvard, and she'll talk about hierarchy construction for fractional quantum Hall states via anyon condensation.
I'm very thankful for the organizers for putting together this nice program. Today I'll be talking about some work that I put out with Ashwin from Harvard and Xiaogang from, which all of you know, earlier this summer on some aspects of the fractional quantum Hall effect and something that has been studied for many decades called the hierarchy construction and kind of reinterpreting it in a modern lens. So some of you might dislike it when I say anyon condensation. So if that applies to you, you can replace that word with gauging a one-form symmetry.
Okay, let's look back on here. Oh, new error, but we have many pointers left. Okay, let's try now. This worked last time, so the others work. And this is it's a bit smaller, but okay. Let's start.
Okay. The fractional quantum Hall effect occurs when you have a thin material and you put it in a magnetic field at low temperatures. And the interesting thing that happens is that when you apply an electric field in the y direction, you get a current in the x direction. And the proportionality of that current to the electric field is the Hall conductance. This Hall conductance is related to the filling fraction nu. And the interesting thing is that this nu is quantized at sufficiently low temperatures and sufficiently nice materials. This filling fraction nu is an integer in some cases, and those are easy to explain with Landau levels. We understand why they're gapped. But when nu is not an integer, then in general we need some underlying non-trivial topological order with anyons to explain this fractional nu. This filling fraction is known as a filling fraction because it's the ratio of electrons to the flux quanta. And shortly I'll review exactly how that's connected to the anyon data. The nice thing about these kinds of systems is that they're actually really observed for many decades now. And you can see that there are not only these nice integers, 4, 3, 2, but also all of these fractions. So at each of these points where it has an arrow and there's a gap because the r-axis goes to 0, then each of these correspond to a topological order, an anyon theory. And this is one of the most convincing examples that we have of realizing anyon theories in the real world. So a question that's very important to condensed matter theorists is when we observe each of these gap states, what is actually the underlying topological order that describes the theory that you have experimentally prepared? So to understand all of the possibilities for how to explain those gap phases, we need to understand topological orders enriched by U1 symmetry. So these are going to be G cross beta tensor categories, supermodular tensor categories because the underlying degrees of freedoms are fermions, electrons, and the G is U1. So we're going to be, in general, working with fermionic systems in this work. And as all of you know, the way to describe the underlying anyon theory is by some set of simple objects, fusion coefficients, F and R symbols. In this case, we're also going to have a special anyon label that braids trivially with all the other anyons, and it has spin -1 is our physical fermion. We also need to add U1 symmetry to the problem. And when a U1 symmetry acts on a system with topological order, it can fractionalize. So what that means is that it localizes this action to this action near the anyons, and because it acts near both A and A bar, this charge conjugate, when it composes, it only needs to compose up to a phase. And for that phase to be consistent with the fusion properties of the anyons, we can, without loss of generality, parameterize that phase by braiding with a particular abelian anyon. So this abelian anyon is going to be labeled V. In the condensed matter literature, people call it the Vizon. So that means that this, because it's given by braiding with this abelian anyon, and if my group is U1, I can apply pi rotation twice, and that should pick up the charge of this anyon. And because this braiding can be non-trivial in general, the charges can be fractional. We can also read off the filling fraction, or the Hall conductance, from this choice of the Vizon. So the choice of the Vizon, its spin, gives you the Hall conductance, the fractional part of the Hall conductance. So this is our set of data, our anyon theory, and how the U1 symmetry fractionalizes, which is given by the choice of the Vizon. And so now we can consider the space of all such theories and go back to our, yes?
Is the H3 class ever an important piece of the data for fractional quantum Hall states?
So in this case, the U1 symmetry will not permute the anyons, and the H3 class will always vanish in these theories.
Even for non-abelian states?
Even for non-abelian states.
Okay.
And among these anyons, we'll have special minimal quasi-holes and minimal quasi-particles. And these are going to be the anyons that have the smallest fractional positive charge and smallest fractional negative charge. And there may be multiple minimal quasi-holes and minimal quasi-particles. These are important because, as I will mention later on, but these are just special anyons in your theory. So, okay, now equipped with that description of the system, we can ask, what is the theory that is most likely to be realized at each of these gapped phases? We can focus, for example, on this simple 1/3 state, for which we can, has been observed for a long time. And one very simple explanation for that gap state is this cyclic anyon theory. I can write down also a Lagrangian for that, given by this Lagrangian density, U1 level 3 Chern-Simons theory. And the anyons are just cyclic, they're abelian, they have these fusion rules and these spins and braiding properties, and you can see that n can run from 0 to 5. The a to the third, where a generates this U1 level 3, is our transparent fermion because it braids trivially with everything else. And if we choose the Vizon to be the generator of this U1 level 3, you can see from the topological spin that we have exactly filling fraction 1/3. So this is a nice explanation for this 1/3 state because it's simple, it has small Carolyn charge, it has small rank. And it's basically the simplest theory you can write down that has this filling fraction. But the problem is that there are many, many theories that I can write down that has this filling fraction because all it depends on is the spin of the Vizon and the spin of this particular abelian anyon. So in general, this is just one piece of data, and it's hard to specify what is actually the topological order, just given this one piece of data. Now let's look at a slightly more complicated theory, this 2/5 state. And you can ask, what is the most likely topological order to explain this 2/5 filling fraction? A story that's been around for a long time, and I'll kind of gloss over this pretty quickly because we have not much time, is that fractional quantum Hall states can come in families. And this 2/5 state has been understood as it might belong in a hierarchy of fractional quantum Hall states. And the idea is that if I start off with this 1/3 state and I tune the magnetic field to be slightly smaller, what I'll do is that we'll change the filling fraction to be slightly larger. So what I'll do is I'll nucleate these minimal quasi-particles because they are my smallest negative charge. And these minimal quasi-particles can condense in the presence of a magnetic field into their own Laughlin state. At the level of you can do this at the level of the wave function in the Lagrangian if you have an explicit Lagrangian. So this is my original 1/3 state, and then I couple it to a background U1 gauge field, and then I insert this current for the quasi-particles. And then I can say, oh, at a mean field level, suppose that this dynamical little a doesn't respond to the insertion of these quasi-particles, then they can act as a background field for these quasi-particles and they can condense. And so then you get this effective field theory, and you can compute, because we have the explicit Lagrangian, all the properties of this theory, and you can show that indeed the simplest possible thing that happens is these quasi-particles will condense into a 1/2 Laughlin state, and then that will give you this nu equals 2/5, and you get all of the anyon properties of that. So this is a way to explain the 2/5 state because there are many theories that can have this 2/5 filling, But maybe this one is more likely because it's closely related to this 1/3 strong plateau that we're pretty confident in. So it has a story. Okay, but that's a little bit unsatisfactory because in order to get this 2/5 state, we needed to use an explicit Lagrangian or wave function, and it's hard to generalize that to non-abelian states. And furthermore, what we're doing is really kind of condensing fractionally anyons with fractional spin into a Laughlin state into the presence of a magnetic field. But the topological operations we're familiar with are stacking topological orders and anyon condensation, engaging one-form symmetries. So then the question is, how do we develop an algebraic framework to interpret this procedure? And so the approach that we have is that we have this C theory, which is our original parent theory. And then we imagine that as we tune the magnetic field away from the original magnetic field, we have an excess of magnetic field. So in principle, we can nucleate this theory D, which has filling fraction nu prime. So the composite theory has filling fraction nu plus nu prime, and we can condense some anyon. So we condense this condensable algebra A. And the idea is that this C theory has these minimal quasi-holes or minimal quasi-particles that want to condense, but they're not bosons, so they cannot condense on their own. So this D theory is necessary such that the minimal quasi-holes or quasi-particles that want to condense in C can bind with something in D such that the composite is a charge 0 boson that can actually condense and give you a different fractional quantum Hall state. Two caveats is that we're working with fermionic theories. So secretly, you can have many approaches, one of which is minimal modular extension to make this story more rigorous. And then the second caveat is that many of us are used to working with Lagrangian algebras, and in this case, it's not Lagrangian, it's just some condensable algebra. So this C stacked with D, and then after the condensation, that's not a trivial state, but a non-trivial fractional quantum Hall state. Okay, so to recap, the idea is that if we tune the magnetic field to be slightly larger, filling fraction goes down, we nucleate these minimal quasi-holes. They want to condense, but they can't condense without something to bind with in D, so they bind with some anyons in D to condense. And then a similar story happens with the quasi-particle hierarchy. So there are, the math is straightforward. You can always find D such that this composite theory has a condensable algebra that includes AH bound with something or AP bound with something. And we also want that to ensure that the anyons that we condense carry 0 electric charge so that we don't have a superconductor. And then we also want this D to have an appropriate U1 factor such that it increases or decreases the filling fraction appropriately. But then even given these requirements, there are many, many possible choices for D. So this is the hand-wavy part where we can only try to find the simplest or minimal D given some physical guidelines, but at the end of the day, we may still end up with many possible options for you to observe in the experiment. Okay, so let's try to reconstruct the Haldane-Halpern hierarchy using this construction, and then we can generalize to non-abelian topological orders. So if you have an abelian topological order, we just need to work with condensable subgroups, which is just a subgroup of the anyons that have trivial mutual braiding, and then the anyons that survive in after you condense are those that braid trivially with all the guys in your subgroup. So we can go back to our favorite 1/3 state. And this guy has a minimal quasi-particle, A to the -1, as charge -1/3. And we can do the simplest thing, which is we just stack with U1 level M for some unfixed M. And the anyons here have spin e to the 2 pi I L squared over 2M. And now we can try to condense this anyon that's a Lagrangian condensable subgroup generated by e to the -1 b to the L. We bind our minimal quasi-particle with some guy in D. And there are two constraints. First, we want this guy to be a boson. And second, we want this guy to have 0 charge. So if you put those two conditions together, we get pretty tight constraints for this M and L. M is and L are given as follows. So if we choose the simplest possible theory, which is choosing n is equal to 1, so we have U on level 15, we precisely recover this 2/5 filling fraction, and the same anyon theory that we had earlier from this effective field theory approach. And you can show that for any parent abelian state, this also produces the Haldane-Halperin hierarchy. So the really interesting thing is for non-abelian states. And these have been observed in experimental systems for many decades now. One very famous non-abelian state is that filling fraction 1/2 plus some integer. And there are three main candidates for what could be realized at those filling fractions. There's the Pfaffian, the interpfaffian, and the PH-Pfaffian. This mod Z2 is indicating that the Ising times U1 level 8 is a bosonic theory. So we're going to condense the fermion, we're going to throw out the anyons that braid non-trivially with our microscopic fermion. All these three theories are very similar in the sense that they have the same filling fraction, but they have somewhat different braiding properties. So they're different topological orders, U1 enriched topological orders. So then the question is, what is actually the theory that's realized when you observe this gapped phase at filling fraction 1/2? And one thing that you can do to give some indication to what phase it is to measure the hierarchies. So you tune the magnetic field to be slightly larger and slightly smaller, and you observe which gap phases you observe. So which filling fractions you see neighboring gap phases at, because different parent phases, because of the different braiding properties, will have different daughter states, as we will see. The simplest, so let's look at the Pfaffian anyon theory. And this guy has these anyons. The psi sigma come from Ising topological order, and the A's generate a U1 level 8. So the fractional charge, we're going to choose the Bison to be this A square, and then the fractional charges are going to be 1/4, 1/2, etc. So the minimal quasi-whole and quasi-particle are non-abelian in this case. And you can see from the spin of the Bison of A squared that this has filling fraction 1/2, as you would expect, because it is a candidate for this 1/2 filling fraction state. So our goal is to condense now this non-abelian guy. And you can actually show that you can't condense this guy by stacking with any abelian topological order. So we can't use this simple trick that we used before where we stack with U1 level m or minus m if we want to condense this sigma A bound with some guy in D. Instead, we have to stack with something that's non-abelian. And the simplest one that we can stack with is this Ising bar times U1 level minus m for the quasi-whole hierarchy. And so, okay, so you can go through the same calculations as before, and what you find is that this m is equal to 8 times 16n plus 1. So plugging in n equals 1 gives you the simplest possible theory, which is Ising bar times U1 level minus 136. So you imagine your D is this crazy large theory that you stack with your original Pfaffian state, and you can condense this very large condensable algebra. And what you find is that the final filling fraction has this rather simple form in terms of n. So if I plug in n equals 1, this big guy will give me 8/17. And you can get the exact resulting anyon theory, etc. So you can do this with all three states, Pfaffian, interpfaffian, and the PH-Pfaffian. And you get different quasi-whole and quasi-particle hierarchies. And the first two were already computed by Michael Levin and Bert Halperin in 2009. They did it from the wave function approach. So you can write down a wave function for these states, and then you can integrate over the positions of the quasi-wholes and quasi-particles explicitly. But that calculation is a lot more complicated than the adding of fractions that we did. And then also, it was hard then to generalize that to PH-Pfaffian because this one doesn't have such a nice wave function that you can write down and do this calculation with. So, and the cool thing is that these filling fractions are actually observed. So you can see here, this capacitance measurement is a measurement of how gapped your state is. So you can see that on the left side, there's a big gap at 1/2, and then they observe smaller gaps at 8/17 and 7/13. So that guy is the Pfaffian. On the right side, there's many different samples, and some of them demonstrate data states at 8/17 and 7/13. Some of them demonstrate it at 6/13 and 9/17. So some of them are Pfaffian and some of them are anti-Pfaffian. And we don't see this pH Pfaffian in any of these examples. But now this is a toolbox which we can, this is a machine you can plug in many of these fractional quantum Hall states that have been most likely to be observed in experiment due to numerical checks and other things. And you can consider the simplest possible D to stack with them and then get the data states so that you can predict, have some prediction for what you might observe on either side of this parent state. And so there are other things to do. One thing that would be super nice would be to see if this story of the hierarchy construction can have some better backing in experiment, because at this point it's still a story, and it's also a bit weird because we have these huge topological orders that we end up stacking with. So not quite sure what those huge topological orders mean, like U1 level minus 136. And then there's also this bigger question of, we can also produce a Jane sequence, which is a different physical picture. But there's many kind of wave function manipulations that people have used in the past in the condensed matter literature, like flux attachment and generalizations of that, and projected wave functions. And in this work, we have an algebraic interpretation for the hierarchy, the Haldane-Halpern hierarchy construction. But what about for all of those other wave function manipulations? And then there's also other properties of fractional quantum Hall states, such as shift, which is basically fractionalization of rotation symmetry, and other spatial symmetries that we have not yet incorporated. But there's probably some way to incorporate them if you have certain constraints on what you condense, such as analogs of this charge zero condition. So thank you for your attention.
Thanks very much for this really nice talk and for keeping time perfectly.
Look at your table. Did you do the story for A3rd?
For what?
For A3rd, the fleeting fraction A3rd.
Oh, 8/3. So 1/3. But are you talking about
Second level 2/3.
Yeah, so there are many, so that's hypothesized to be non-abelian, right?
Abelian too.
But it could also, so the abelian one is the Haldane-Halpern. For a non-abelian,
It's not there.
it's not here. It could be the particle hole conjugate of the SC2 level 3. Right? And so we have those calculations, but it could also be, and I guess those would be the simplest maybe.
Third is there. So do you mean some of the 2/3 is SU2 level 3?
So we ask you to level 4. There are 3 obvious states. There are 3 obvious topological orders.
So you said it's SU2 level 4.
It's bad, but I just mentioned, there's a paper by me and Shankar, for numerical simulation. There are 3 obvious candidates for A3rd.
Okay.
But actually it's a 2/3, right?
It's 2/3 second.
It's 2/3 second. So I see. Yeah, we only look at the SU2 level 3, yeah.
So just, there's a Lafnin state, there's SE2 level 4 Reid-Rezai, and there's a spin singlet due to LDR down. So we did the numerical simulation, we cannot tell the difference.
Yeah, we can chat more about that, but we didn't do those calculations.
Okay, there's a question in the back. Jonathan?
Thanks for the nice talk. Sorry if this question is a little too naive, but it sounded like you had different choices for the D that would produce the same. So suppose you had D and D prime. What physically distinguishes the choices, or you don't care about which one you pick?
Yeah, so generally different choices of D will produce different daughter states. And so you might ask, what is the choice of D that produces the most natural daughter state, in the sense that the daughter state is simple, it has low rank, the difference in chiral center charge between the daughter state and the parent state is minimal, things like that. So unless you choose a D that differs from D prime by just something like that's more equivalent to vacuum, then they will produce different daughter states.
Is it clear there's a D?
Sorry?
Is it clear there's a unique D?
There is not a unique D, in general. Do you mean a unique D that produces a given daughter state, or do you mean like a unique D?
C times D mod A, and then you had a C times D mod A, and then you picked the D that you wanted in order to produce the correct thing, right? So is it clear that that D is unique? Or sorry if this is naive.
Yeah, so first of all, we don't know what the correct thing is, so we can just hypothesize what the correct thing might be. But then in that case, it's not unique, but there's a minimal one.
You showed that the Pfaffian and anti-Pfaffian can be realized in two samples. I was wondering what's the difference between these two samples? Are these two different materials?
Yeah, so here in this case, they're just 1/2 plus some different integer. And so the idea is that, my understanding is that the particle hole symmetry can be spontaneously broken. So in some samples, you might realize the Pfaffian, and other ones you might realize the anti-Pfaffian. And it might also depend on, this integer part of the filling fraction as well. At least that's what differentiates these samples on the right-hand side here.
But they're for the same material.
Actually, they are same sample, but this is the observe different plateau.
Yeah, so these are the same, this is the same sample, but just different integer part.
Different integer parts.
Okay.
Number 2,
I fail to see the role of D. I understand that it's used in an intermediate step because it's not at the starting point and it's not at the end.
Yes.
So does it have an intrinsic meaning in the physics, or is this a mathematical tool that allows you to get the final answer?
Yeah, so I interpret it as a mathematical tool, like a virtual state that allows me to get the final answer, but may not have like a physical detectable meaning.
So asking it differently, imagine that we start from the same state and we end up with the same state, and you and I use different D.
Yes.
Will there be any experimental difference between the two stories or not?
I would not imagine there to be, but maybe that deserves thinking a bit harder about it.
Is it possible to apply your strategies to non-unitary CFT and the corresponding topological order?
So in principle, you can always take a non-unitary CFT and play this game of stacking and gauging one-form symmetries. But I'm not sure, in what physical context that would.
Yeah, for example, if we stack two Garfinian theory,
Yes.
we may get the spin 1 Garfinian, and more or less, spin 1 Garfinian is more stable than single Garfinian I'm expecting. So is it possible to explain such phenomena in your formalism?
Yeah, so if you have a topological order that's more stable than another topological order, then I'd imagine that might be because there's some one-form symmetry that you can gauge, so one is not minimal in that sense. Is that the story that happens here, or is it? I'm not,
Okay, we can discuss later, thanks.
Okay.
Okay. All right, let's thank Carolyn again for his really nice talk.